This is the second video on the analysis of directional data. The topic here is hypothesis testing, and I'd like to talk about three different types of tests. The first test is for complete randomness in the orientations of a sampled population. If that test results in the finding that the population is unlikely to be randomly oriented and have a preferred direction, then we can test whether that direction matches uh, another direction. So it's a test for a specific direction. And then the last test is a two-sample test of the equivalence of the mean directions of two sampled populations. Now, when we do any hypothesis testing, we must rely on theoretical probability density functions to, for example, evaluate probabilities or significance levels. For example, the Gaussian PDF was highly used in non-oriented data. For oriented data, a widely used PDF probability, well, I guess a widely used probability model is the von Mises distribution. So what makes directional data require a different distribution than, for example, the Gaussian distribution is, of course, the values range between 0 and 360 or minus 180 to 180. They have a finite range. Now, the von Mises distribution is the two parameters that characterize the von Mises distribution are the mean angle, theta bar, and then kappa, which is the concentration parameter. And that controls the spread of the distribution. So the von Mises distribution is shown in this diagram from Davis in two different ways. The first is a polar histogram, and this polar histogram has an infinite number of pi's, so the pi's are just outlined. And then the lower diagram shows it in a more sort of traditional form, looking more like a histogram. So in both cases, the mean direction is northward, I guess, on the plot. It's upward on the plot. And when kappa, the concentration, is 0, then all the angles are equally probable. So the polar histogram shows just a unit circle, meaning all the pi's have exactly the same length. And in the diagram below, the kappa of 0 would be represented by this straight line right here. Now, as the concentration goes up, so let me write that down here. So kappa equals 0 means perfectly random orientations, and then as kappa goes to infinity, then the concentration is very high. Or, in fact, if kappa equals infinity, then the distribution approaches a uniform direction. So you can see here as kappa starts off from reflecting a random distribution to greater concentrations, the polar histograms become more focused to the direction. In this case would be 0 degrees, 0 azimuth, and this is also illustrated in this lower diagram with the probability increasing and focusing towards 0. So the first test for randomness may have a can be described as having a null hypothesis that kappa equals 0. That is, the population has a random distribution, and of course the alternative hypothesis is that that kappa is not equal to 0. Kappa is greater than 0. And this is a very simple test. You just simply compute the normalized length of the resultant vector and compare that to a critical value of r based on the specified level of significance. And of course, we need to consider the number of measurements in our sample. So in Davis's example, he looks back at these glacial striations. We talked about those in the previous video. And he again sums the unit vectors to get the resultant vector. And his resultant vector, so this is the example for the glacial striations. And the resultant vector had a length of 40.82. And then he normalized R by the number of measurements. And that came out to be about 0.8. There were 51 measurements. And let's say alpha is equal to 5%. And on the PDF on the website, you can refer to the very back of it and look at table A10 of Davis. And this table gives you the critical value of the normalized vector. So we have about 50 measurements in our sample. Our significance was 5%. So the critical value is 0.24. And we find that R is much bigger than 0.244, meaning, oh, I'm sorry, I should be looking at the normalized value, not the non-normalized value. So R bar is greater than 0.24. So the normalized resultant of our sample is too large to have come from a randomly oriented population. And so we have to reject H0, reject our null hypothesis that the glacial striations throughout the whole area are random. So now that we've determined the population is unlikely to be randomly oriented, that is, there seems to be evidence for a preferred orientation of our glacial striations, we then might be interested in knowing what the preferred direction is, the true preferred direction. So the next exercise is to compute the confidence interval on the true mean directions. And from that confidence interval, we could test whether the true mean direction matches another direction. And in Davis's example, he notes that in the area of the glacial striations, there's a topographic depression. So he was interested in knowing whether the mean direction of the striations matched the azimuth of the topographic depression. So to compute the confidence interval of the true mean direction, that's capital theta with a bar over it, we need the measured mean of our sample plus and minus the standard error of the true mean, and here we're going to use the z statistic. So this is the true mean of the population. This is the sample mean. SE is the standard error on the sample mean. That is, if we repeated our sampling multiple times, we would get different values, and the standard error describes the spread of those values. So, of course, we've already computed our sample mean, and our normalized resultant vector. So from our bar and table A.9, then we can estimate kappa. Again, remember that our bar is a measure of the variance of the sample, and from the variance of the sample, we can estimate the variance of the population using the von Mises distribution. And the variance of the population, or the von Mises distribution, again, was described by the concentration parameter kappa. And so it turns out that the standard error on the sample mean is equal to 1 over the square root of n. We see that term again as we have before, times the length of the normalized resultant vector times the concentration parameter. And so you can see, of course, as the number of samples go up, the standard error on theta bar decreases, as the likewise, as the resultant vector gets longer, the standard error decreases, and as the concentration parameter increases, the standard error decreases. So this allows us to define the probable direction of the true mean with the standard error. And of course, we have the z statistic, which comes from the Gaussian distribution, and that's a function of our significance level. So now to test whether theta bar matches that of our topographic depression, let's just call that theta bar 0. We simply answer the question, does the test orientation fall within the confidence interval? Or equivalently, we can just calculate a z statistic. Which is the difference between our sample mean and our test value, our test direction divided by the standard error. And we see if that z-value is actually the absolute value of that z-value exceeds the critical z-value. So another test that can be performed to compare an observed sampling to another theoretical distribution, or even another sample, is the chi-squared goodness of fit test. And this test applied to directional data is much like what we've seen before. So the first step is to divide the unit circle into, say, k, not kappa, angular bins from 0 to 360 degrees. And the number of bins should be between the sample size divided by 15 to the sample size divided by 5. So that's the limits on the number of bins. And then we count up the number of observations, observed angles in bin J, in each of the bins. And we compare that with the expected number. So the chi-squared is equal to the sum over all the bins of the observed numbers of directions in bin J minus the expected, and that difference is squared and summed, and the ratio is taken with the expected number, and that ratio is squared to give chi-squared. And the degrees of freedom is nu, and that's equal to the number of bins minus 1. And we can compare our chi-squared statistic with the critical chi-squared statistic. So we could use this, for example, to test whether the data set is random or kappa is equal to 0, in which case EJ, the expected number, is simply n, which is the total number of measurements divided by the number of bins, right? That's a uniform distribution. Alternatively, we could do a test of the preferred direction. That is, if the population sampled has a mean equivalent to that of a known or theoretical value. So to do that, you have to first compute the concentration parameter from your sample, and you would use tables to compute what the expected value is for each bin, given the theoretical mean and kappa. And page 326 of Davis gives references for computing the expected number. And there's also, you can also Google, search on the web for MATLAB statistical toolbox for circular data. It's called, let's see, what's it called? It's called the Circular Statistics Toolbox. So I'm going to conclude this this video on hypothesis testing. We've looked at a way to test for randomness in a data set, and we've also looked at two ways for testing for a specific direction. The two-sample test of equivalence of means will be covered in the next video.